Good day everyone. Today we are diving into the world of microchannel heat exchangers. They are tiny but mighty devices that revolutionize heat transfer. And by the end of this presentation, you should hopefully see why they are so important. So imagine you are trying to cool down a boiling hot cup of tea by blowing on it. It will take a while. Now imagine if that tea was spread out into tiny little channels. It will cool way faster. And that's exactly how microchannel heat exchangers work. So they are compact devices with super tiny channels, typically less than 1 millimeter in diameter. The magic behind them is that they provide a massive surface area compared to their volume, so they make heat transfer super efficient. A quick history lesson. In 1981, two researchers, Takaman and Pease, realized that these tiny channels could revolutionize cooling, especially for computer chips. And right now, in status quo, they are not only used for computer chips, but they are used almost everywhere. So from air conditioning units to car radiators. Alright, let's get a bit technical, but in a fun way. Heat moves in three ways: conduction, convection, and radiation. Microchannel heat exchangers mostly rely on conduction and convection. Conduction being heat moving through the walls, and convection being heat moving between the fluid and the walls. A key player here is the first law of thermodynamics, which is basically the no free lunch rule of energy. That is, energy isn't created or destroyed, it just moves around. In a microchannel heat exchanger, you can calculate the transfer with the heat equation. You see, so you can calculate the transfer with this heat equation, and the Q is equal to mCp T in minus T out. The Q is the heat transfer rate, how much heat moves. M is the mass flow rate, how fast the fluid moves, and Cp is the fluid's specific heat capacity, how much heat it can carry. T in and T out are the temperatures before and after heat transfer. What this equation does is that it basically tells us hot fluid gives energy to cold fluid. No heat is lost, it's just transferred efficiently. Now you might think, just make some tiny channels and you are done. But the shape of these channels really matter. So there are curved ones, there are straight ones, there are grooved ones. All are designed to mix up the fluid and boost heat transfer. So it's more or less like stirring tea to cool it faster. The materials that you use are equally another big deal. And the common choices are aluminum and copper for their excellent thermal conductivity. But ceramics are also used, and composite materials are also used, especially for extreme environments. What advantages then do we get when we use microchannel heat exchangers? And they are the heat transfer ninjas. So thanks to their size, heat moves faster. So what you can get as a benefit of using it is the increased efficiency when it comes to the transfer of heat. So there is more transfer with less energy. It means that you get better thermal performance. So the second benefit is that lower refrigerant charges and reduced air side pressure drops are benefits that you get from this. As part of the slides, I would show you some of the disadvantages or some of the problems that you can have when you are using microchannel heat exchangers, and then you would understand the whole idea of the pressure drops there. But the third is their compactness and the way in which they are designed, in a way whereby they are able to save space. So they save space and weight, and that is really great for industries like automotive and aerospace. You don't want to have so many things in one industry just taking up space. And so about the compactness, the lower refrigerant charges, that helps reduces the environmental impacts. So then the final thing then is that they have fast responses. So they are ideal for systems that deal with rapid temperature changes, and therefore they have a good thermal response. So now let's look at the challenges and considerations. Now, not everything is sunshine and rainbows. I mean, with great power comes, well, engineering headaches. And then the first of these engineering headache is the pressure drop. So small channels mean higher resistance. So fluids need more pumping power. And I would explain this whole second law thing. I'll come back to it. So there is fouling and fluid quality. Narrow channels would demand higher quality fluids. So think of it this way. If you have a tiny straw, even a small particle can clog it. What that means is that the fluid that will be passing through the microchannel heat exchanger in of itself should have higher quality, because you don't want to have a lot of blockages happening in the microchannel, because then it means that you can't really transfer fluid and all of that sort. Another one is the manufacturing complexity. So making precise small channels is very tough. The final thing is the corrosion risk. And these systems need proper coating so that you don't have a lot of corrosion. So now let's break back in the second law of thermodynamics, which basically says that entropy most likely always wins. So every real process creates some energy loss. And in microchannel heat exchangers, that's measured using this entropy equation, where the S gen is supposed to be the entropy generation rate, S in, S out, entropy flow at inlet and outlet, and the T is the absolute temperature. What this tells us is that minimizing entropy generally leads to better efficiency. The challenge is that engineers must optimize designs to keep entropy low and efficiency high. What are the applications of microchannel heat exchangers in the industries? So, where do we actually use these tiny heat movers? And one of them is electronic cooling. So, they keep your laptop and high performance processors from overheating. They are equally used in automotive and aerospace. So, they are used in radiators and turbines and turbine engines. And equally in refrigeration, they are found in air conditioning units for better efficiency, and heat pump systems, so perfect for eco-friendly refrigerants like R32. Real world example is Caltress microchannel coils, and they are now a big deal in modern HVAC systems, making them more efficient and environmentally friendly. Okay, so academic research shows that these systems are heavily used in refrigeration, air conditioning, and even nuclear power plants. Recent innovations include 3D microchannel heat sinks with turbulators, which improve heat transfers even further. Companies like Ultra, once again, are scaling up microchannel technology, proving its reliability in extreme conditions. Where are we headed next? Let's peek into the future. So multi-scale optimization. You are using fractal and constructional designs for smarter efficiency, and this will happen in wider scales. Two-phase flow enhancements. So research on boiling and condensation in microchannels is pushing the heat transfer boundaries. Smart integration. That is, you are embedding the sensors for real-time monitoring to maximize performance. Okay, so let's wrap things up. Microchannel heat exchangers are compact, powerful, and widely used in industries like electronics, automotive, and HVAC. While they offer high efficiency, they come with design challenges like pressure drops and fouling. But with ongoing research and innovations, we are heading towards even better designs with higher performance and smarter integration. And yeah, these are references that you can check out, references that I used, I mean my team and everyone used for their research. So we put them together and you can check them out for further details. Yeah, thank you very much for your time.